Okay, Lawrence, are you ready? He seems to be frozen.
Mm. Mm.
Something untoward just happened.
Okay, right, you're back on another screen. Okay, shall we start, Lawrence?
Yes.
Okay, great. So welcome everyone to the third day of our Biophysics in Africa Zoom conference. It is my pleasure to host or to chair today's talks. And we are starting with a very special talk from Prof. Jörg Innerlein from the Georg August University in Göttingen, Germany. So I'm very much looking forward to this talk. And Jörg, the floor is yours.
Thank you so much. I feel very honored to be given the opportunity to present my work here in this conference. Thank you, Tjad and colleagues. And my topic will be, as you can see, fluorescence lifetime super resolution microscopy, and this is summarizing the work of our group for the last something like 15 years. And as you can already see in the starting slide, so the main player is the single fluorescent molecule, and you see here the electric field distribution around such an emitting molecule. And I will give you more details what it is about. So the first topic I will present here is about so-called image scanning microscopy. And to understand what I'm talking here is to look into the resolution limit of microscopy. Let's start very simple. Let's assume we have a wide field microscope. Here you see the objective, which is collecting the light and then directing it towards the detector. And we have here in this animation, this situation where we have two coherent emitters, so 2 point emitters very close by. What you see here is the electric field distribution, which is generated by these emitting point emitters. And what you can see here in this movie is how this electric field distribution is changing when the distance between your two emitters is getting smaller and smaller and smaller. So in the beginning, when the distance is relatively large, you see a lot of these the destructive interference lanes where there is no light emission. It is like the double slit experiment from the 19th century. But when the distance between these two point emitters becomes smaller and smaller, then these destructive interference lanes, they are moving to higher and higher angles. And at the critical distance between the two emitters, the first destructive interference lane is hitting the edge of your objective. And then the objective is only detecting a continuous wavefront with no structure anymore, and it loses completely the ability to distinguish between the emission of a single or multiple emitters. And by doing this very simple calculation, you then can find what is the critical distance so that the first destructive interference is exactly at the angle, half angle of light collection. It gives you then famous Abbe's resolution limit, which tells you, okay, if the distance of my two emitters is smaller than the wavelength of light divided by 2 times the refractive index of my medium, and sin is big theta, where big theta is the half angle of light collection, then I cannot resolve these two emitters anymore. So this was the status of microscopy for hundreds of years. Of course, and in the 20th century, a new modality came into play, which is confocal scanning microscopy. Which is working in a different way. So in the confocal scanning microscope, you are focusing light in a very tight focus into your sample. Then you scan with this focus your sample point by point, and at each scan position, you record the fluorescence signal which is excited. Of course, I can again ask what is the spatial resolution of such a microscope. It is determined here now how tightly I can focus light into a tiny focus. And this is shown in this animation again, which is shown here is how this focus diameter, this is the intensity here, here's electric field, how this focus is changing in size when you have a higher and higher numerical aperture. And as you can see again, of course, then there's a limit how tight we can focus light. And when you do the mathematics, you will find that the lateral resolution limit of such a point scanning system is basically the same as in wide field microscopy. So the confocal microscope under normal conditions is not improving your resolution. The main purpose why people invented such a microscope was to imbue the microscope with three-dimensional sectioning capability. This is done by this confocal detection here, which is restricting light detection from planes far away from the focal plane. But that was the main purpose. And when you look now at the numbers, what is in this diffraction limit possible in resolution, then you have this famous picture here. On the x-axis, you have the numerical aperture of your objective, which is a proxy of the half angle of light collection. And here is the resolution achievable in nanometers. And then, of course, we have a lateral resolution limit, which is also dependent on the wavelength. But there's also a similar equation here on the right-hand side, which for the axial resolution of the confocal microscope. And in the best cases, let's say here 1.2 highest aperture, we then can achieve something like 200 nanometer lateral resolution or something like 600 nanometer in the axial direction. However, and this is now for the confocal microscope, it was long known from the very beginning that if you would make your confocal aperture smaller and smaller and smaller, at some point you also start to improve the lateral resolution. This is shown here. What you see here in this graph are 6 different point spread functions calculated for different pinhole sizes for 60 times confocal microscope, starting with a very large diameter here in the top and then going down to something like an infinitely small pinhole. 1 micrometer is very close to 0. And of course, as you can see, when you make your pinhole smaller and smaller, then also at some point you start to make your point spread function smaller laterally, which would result in a resolution improvement. So why don't people do that? Yeah, the answer is quite simple. When you make your pinhole smaller and smaller, then your detection efficiency goes down also to 0. For example, for the 1 micrometer pinhole, you have basically no light left which could be detected. So this is already starting at relatively large pinhole sizes. So closing down the pinhole is certainly not a very good idea for getting a higher spatial resolution because you lose tons of light. However, this physics was then somehow the inspiration for us to think about whether there is a clever way how to design a confocal microscope with something like an infinitely small pinhole like this one here, but with no light losses. So how can you do that? And the idea is depicted here in this schematic. So again, here you see our standard confocal microscope, excitation light. Here's my sample objective. Here's the dichroic mirror. Here's the confocal pinhole. Here's the detector. So the idea was to kick out this whole part here, which is confocal pinhole, relay lenses, and light detector, to kick it out and to replace the pinhole here by an array detector in such a way that each pixel of this array detector is acting as something like a union of a very, very small confocal pinhole and a light detector. The size of this confocal pinhole, of course, is the size of 1 pixel, and the pixel is light sensitive, so that would be something like the union of this whole setup, what you see here downstream. However, now what we have no light losses, because whatever light comes from your sample, it will somewhere hit your light detector. So the idea is now the following: you take your confocal microscope as before, so with a focused laser light excitation, you scan point by point your sample. And instead of recording only 1 scan image with 1 detector here, you are now recording something like, let's say, 10 by 10 scan images in parallel. So every detector, every single pixel on this detector is recording its own scan image. So in the end, what you get is something like 100 scan images, and you have to think about how to compose them into a final high resolution image. So simply by adding all the images up is not a good idea, because every pixel has a slightly different viewing angle onto your sample. This is a parallax effect. So when you would simply add all the scan images recorded by every single pixel here into one final image, you would see something very blurry, which is shown schematically here. So we have to think about a clever way how to superimpose all these images to get a sharp and ideally then doubly resolved image. So how to do that? So let's simply look how the scan image recorded by 1 pixel is generated. So this is, for example, we consider 1 pixel on our array detector, which has a distance s from the optical axis. This should be the optical axis here. This is the distance of this 1 single pixel we are now considering. And there are 2 things to consider. The first one is, how good do I excite fluorescence in my sample? And of course, this is dictated by the excitation intensity distribution, which is this blue curve here, and which is, of course, on the optical axis. However, now the second point is, because our pixel is so super small, It has its own detection efficiency, which is also spatially dependent. This is this orange curve here. So this orange curve is describing how well my pixel is detecting fluorescence from the sample. Of course, the point spread function of the scan image recorded by this pixel is the green curve, which is the product of the blue and the orange curve. Now, of course, this green curve has a smaller diameter than the blue and orange curve alone, which is exactly the idea of this resolution enhancement. But what is also important, the peak position here, the center position of this green curve is roughly in the middle between the blue and the orange curve. And this gives us the recipe how to superimpose all the scan images to get a sharp and high resolution image. And the idea is the following. What we do in practice, we are positioning our focus into the sample. We record a small image of the generated fluorescence, and then we reshuffle the signal by 1/2 towards the optical axis and add it to the final image. And then we go to the next scan position and repeat this whole process. This is called also pixel reassignment. This is the whole idea of this method, which we call image scanning microscopy. So you are scanning your sample with a focused laser beam, but you take at every scan position a small image, you do the pixel reassignment, and then hopefully you will get a high resolution image. So the first realization of this idea experimentally was in 2010 with a home-built system where we simply replaced our single photo and avalanche diode here by a whole EMCCD camera, and then recorded indeed at every scan position a small image and did this kind of software-based pixel reassignment. And the result is shown here. So what you see here is a confocused scan image of two fluorescent beads, which are normally used for checking the quality of imaging of your microscope. So fluorescent polymer beads of a very small size. This is here 1 micrometer. That would be the diffraction limited resolution in a normal confocal microscope. And now after this image scanning trick, you see that indeed my images got smaller. And if you do mathematics, you can check it. It's a nearly twofold improvement in resolution. When we published our paper, then we had to learn that this idea was not new. It was already published many, many years before in 1988 by Colin Shepard as a theoretical proposal. So it was a 2-page paper in a journal which is no longer existing anymore, and which is describing exactly this idea for how to improve super resolution, also how to achieve super resolution in confocal imaging. Our setup when we did it in the first time was very slow because we had to use a very slow EMCCD for recording. Then fortunately, Carl Zeiss Jena took up the idea and then they replaced their single detector by a multi-detector photo multiplier tube, which can record images with extremely high speed. And they are now, for example, commercializing the system under the name Ariscan microscope. And to give you some impression how important this doubled resolution enhancement is, this is here data from Carl Zeiss, where they are showing mitochondrial network in a living cell. On the top, you see a vertical, horizontal cross-section of this microtubule network in normal confocal operation. And here at the bottom, in this image scanning microscopy operation with this twofold enhancement. I hope you can indeed appreciate that this twofold enhancement is really important and gives you a lot of details because many biological structures are exactly at this edge between 200 and 100 nanometer. That was the first part of my presentation. The second part is now coming to this fluorescence lifetime issue and also combining it with a method which is called single molecule localization microscopy. Also, image scanning microscopy is a very powerful method, and the good thing is that you can upgrade any confocal microscope with this method in a very simple way to get a doubled resolution. There is, of course, a limit still of the resolution doubling. You cannot go beyond 2 times. So, of course, then people started to think about how to get better. And one of the most popular methods of real super resolution microscopy, much beyond the diffraction limit, is so-called single molecule localization microscopy. And the idea is the following. Let's assume you have in your field of view only a single fluorescent molecule. You know exactly there is only one single molecule in your field of view. Also, the image of this molecule is shown here by this white somehow Gaussian distribution will be dictated by the resolution limit. So that means the image of your molecule, also the molecule itself is only something like 5 angstrom, will appear on your screen as something like 200, 300 nanometers. But because you know that there is only a single molecule in the field of view, you can pinpoint its center position with a much, much higher accuracy. And the rule of thumb in ideal conditions, you can even then show that this localization accuracy is something like the standard Abel resolution limit, but now divided by the square root of the number of detected photons. That means by collecting enough photons in the image of a single molecule, you can pinpoint its position with a much, much higher accuracy than the resolution limit of your microscope. And this is the basis of this idea of single molecule localization microscopy, which was first invented by Eric Betzig and Xiaowei Xuang. At the same time, Eric Betzig then got a Nobel Prize for his part, Xiaowei Xuang unfortunately not. Betzig called it the photoactivation localization microscopy. Xiaowei called it stochastic optic reconstruction microscopy. And STORM, I would say, is nowadays the much more popular method than PAL. So the idea is the following, that you label your sample with fluorescent dyes. Then you have some trick to switch most of the molecules into a dark state, that you then switch on only a very little subset of your molecules, so that you can indeed see individual emitters in such an image. Then you localize the positions of your emitters, you switch them off, you switch on another subset of molecules, you do that again and again, many thousand times. In the end, you get a high resolution image. And to show you how far we meanwhile got with this method, I want to show you some data from my lab. That was a collaboration with Mark Bates from the EF Nano Institute here in Göttingen, where we were imaging with this method single virus particles. In this case here, T4 phage particles, which you see here. What my postdoc, Ignacio Galea, was then achieving is to find a protocol how to immobilize these particles in a very well-ordered manner, that they really stand up as a tree forest on the surface. And here you see then 2 of them. And then what we did, we recorded 3-dimensional single molecule localization images of these particles and then superimposed them. And this image here is then basically the final high resolution image, which is averaged from something like 50 particles. And it gives you some impression how far we are now with this kind of method in resolution. We are coming close to electron microscopy images. So far, so good. That is the idea of single molecule localization, but then we wanted to combine this idea with lifetime imaging, fluorescence lifetime imaging, which is not so easy, because all these images, what you see here in the classical single molecule localization microscopy, is normally done with a standard wide field microscope, simply using a sufficiently sensitive wide field camera. However, fluorescence lifetime is a very interesting additional property of fluorescent dyes, which can be used for multiplexing and also other purposes I will show you later. So we wanted to realize the single molecule localization microscope with lifetime capability. And what we did is we said, okay, why not using a rapid, optimized, fast scanning confocal microscope for doing the same trick as people normally do with wide field microscopy in single molecule localization. So we realized an extremely fast scanning single molecule sensitive confocal microscope. This is simply a test sample here where we labeled a tubular network in a cell with a fluorescent dye. This is the intensity image, it's the lifetime image, also showing you very nicely that we have a very homogeneous here lifetime distribution in such a cell. And then we use such a system for doing exactly what people normally do with wide field. We did single molecule localization microscopy. So when you look here at these movies, here's a STORM image. This is this classical method from Xiaowei Xuang. Here is another method which is called DNA paint, which is very similar but uses a different mechanism for inducing blinking of molecules. This is here the tubular network. Here we look at chromatin labeling. And you see here these single molecules coming up and then again disappearing, and we do this localization. These are the blue dots here. But now, because we are using a scanning microscope, we can also, for every single molecule, we can determine a fluorescence lifetime. So for that, we use a pulse laser and then classical time-correlated single photon counting for calculating fluorescence lifetime values. And these lifetime values are histogrammed here. So what you see here is a histogram of the lifetime values for all identified and recorded single molecules in this sample here, or here in this sample for all the single molecules recorded here in this sample. And we can nicely see we have a very perfect this distinction between these two samples, because here it's a short lifetime dye, Alexa 647. Here it's a long lifetime dye in the sample, ADO 655. And also the width of these distributions is basically short noise limited. What these images are also showing here again is how good the resolution is improved by single molecule localization. Here, this is the normal resolution in the confocal. This is the super resolution where we come down to something like 20 nanometer lateral resolution. Again, here also for the chromatine. Here on the right hand side, you see the standard confocal resolution, and here is the super resolution. So far, so good. So why are we so much interested in lifetime? This is another story I want to present here, and this is called metal or graphene-induced energy transfer imaging. As I have shown you in the beginning, there is this classical resolution limit, which is laterally roughly 200 nanometer and axially in the order of 500, 600 nanometer. So there is a huge discrepancy between lateral and axial resolution. Unfortunately, also for most of the super resolution methods, even for stat microscopy or for single molecule localization microscopy, this discrepancy still persists when we go to super resolution. So we were thinking about an idea, how can we improve the axial resolution of our microscopy? And the idea comes from spectroscopy. So we are basically a spectroscopy group from the origin. And this is shown here in this schematic. So when you take a standard glass cover slide and you cover your cover slide with a very thin metal film, here in this case, let's say 10 or 20 nanometer gold film. And then you take a fluorescent dye in your sample and you are approaching this metallized surface. What you will observe is a very strong modulation of your fluorescence signal due to energy transfer from your dye molecule to surface plasmons in the metal. And this is shown here in the case for lifetime. So what you see here is the calculated lifetime of a fluorescent dye when it comes close to this metal film here in a range between 0 and 300 nanometers. And what you see here, of course, in the near field regime, so below 200 nanometers, that you see a very nice monotonous decay or decrease of fluorescence lifetime when the dye comes down to the surface. The mechanism is very similar to first resonance energy transfer, where we have a donor molecule and acceptor molecule. Here, in this case, the acceptor molecule is replaced by this metal film, which makes also the interaction range much, much bigger. Yeah, in FRET, you have typically only 10 nanometers. Here we have something like 200 nanometers dynamic range. But the idea is the same. We can now use the lifetime information here to then back calculate the distance of a molecule from the surface. So we call this idea metal-induced energy transfer imaging. And the setup in the end, what you need is quite simple. So you need cover slides which are covered with a very thin gold film. It's the only prerequisite. Then you can do your standard cell sample preparation as before. And of course, you need a microscope which is capable of fluorescence lifetime measurements, which is in our case a standard pulsed excitation laser confocal microscope. So to show you how it works, it was the very first publication nearly 12 years ago, where we labeled cancer cells with a fluorescent dye, plasma membrane labeling, and then we put it onto our microscope with this gold-covered cover slide, and then we calculated the lifetime value. We converted the lifetime values back into a distance of the membrane from the surface. So what you see here is a topography of the basal plasma membrane of these cells. As you can see, it's a live cell experiment. So the good thing is that this method is completely compatible with any cell preparation or life cell conditions. And this is now here in false color, the distance of the membrane from the bottom. And I think you can already see that now the resolution along the z-axis is much, much bigger than the standard confocal microscopy. And to estimate how good it is, we have then done some test measurements here where we have simply a standard gold sample with a spacer layer, and here is a very thin film of fluorescent dyes, and it is then the corresponding calibration curve. And what this curve is showing us in the end is that when you, for example, when you have something like between 5 to 10,000 photons per point measurement, then you get an X resolution in order from 2 to 4 nanometer. So the X resolution now is extremely high. And now coming back to single molecule localization microscopy, Of course, we want now to combine this extreme high axial resolution with the superb lateral resolution of single molecule localization. And this is then basically this metal-induced energy transfer storm microscopy. What we show here is an experiment again on microtubules. We have labeled microtubules here in a fixed cell. Then we have taken lifetime images with our confocal microscope. We have done the single molecule localization trick. So it's a storm experiment that gives you this very high lateral resolution in the order of 20 nanometers. And then we have used the lifetime to calculate all the distances from the surface, which is then here shown by this color. And here for two positions in the microtubules, you see now here exact cross sections. Now, of course, it's very noisy. So we are limited by the label density of our sample, but I hope you can already appreciate that we indeed can see the hollow structure of the microtubules in such a setup. Why is it also interesting? Because we can even go one step further. We can replace the metal by something which is called single sheet graphene. That was another Nobel Prize a few years ago for the discovery of graphene, which is this single sheet of hexagonal carbon atoms, which also has a very strong quenching property. It's not a surface plasmon, it's an exciton excitation. The mechanism again is very similar to first the resonance energy transfer, but now the acceptor is the super graphene molecule basically. The distance now, the interaction distance is much smaller, only something like 30 nanometer, as you can see here. Also some technical detail, the quenching curves, they also depend on the quantum yield. This is here for 100% quantum efficiency die. This is for 10% quantum efficiency die, but these are technical details. The main message is that now we can have even a much higher resolution with this method. And this is shown here where we imaged single molecules. These are single molecule data at different distances away from the graphene. And this is for 10, 15, and 20 nanometer. And these lifetime plots here, this is the fluorescence lifetime plot, as intensity versus delay time in nanoseconds, is showing you that by moving our molecules only by 5 nanometers away from the surface, we get a huge change in a lifetime. And why is it so important for biophysics? Because we can now even look into single lipid bilayers, hoping that we can distinguish between the upper and the lower leaflets. So the experiment, what we then did is we prepared supported lipid bilayers. We labeled the head grooves with fluorescent dye, the same fluorescent dye, then did a long lifetime measurement, and then obtained, of course, a bi-exponential decay because the dyes in the top have this longer lifetime than the dyes at the bottom due to this graphene-induced quenching, and then calculated distances between the two leaflets, and this is shown here. This is showing you the 5.5 nanometer or the 4 nanometer here, the distance between fluorescent dyes in the top and the bottom leaflet for purely DOPC bilayer or DLPC bilayer. And we also compared with small angle X-ray scattering measurements and find a perfect agreement. These numbers here for X-ray, of course, have to be smaller because they measure lipid head group to lipid head group, whereas we are measuring fluorescence dye to fluorescence dye distance, which is, of course, bigger because the fluorescence dye is coupled to the head group with a linker and also has its own size. And it was then published a few years ago, first time. And to show you one example, where we now apply it for biophysical measurements. Here we studied the impact of cholesterol on lipid bilayer organization. So we had the 3 different dyes, 2 saturated and 1 unsaturated lipid bilayer. And then we added here cholesterol from 0 to 44 mole percent and looked at the thickness of these bilayers. And what is really important, these measurements are in the end plain simple. You need this graphene substrate and the rest is lifetime measurement and simply then data evaluation. And you can see here, for example, that for the saturated lipids, we have something like a swelling of the bilayer by 1-2 nanometer. Whereas for the unsaturated lipids, we see something like a phase transition reorganization of the bilayer. So first swelling and then again reduction in size. And to also show you that this method is super powerful also for live cell or live living biological samples, this is a study where we were interested in single mitochondria. So we had a protocol to isolate mitochondria from a cell in a physiologically living state. We labeled the mitochondria with internally and externally with 2 different dyes. We put it on our graphene sample. again did this kind of graphene-induced energy transfer measurements, and then could compare what is happening is when the mitochondria are in a resting state with no respiration buffer, and after adding respiration buffer that the ATP synthesis can start. And what we then see is that the outer membrane, of course, is not changing its distance to the graphene, but the inner membrane on average comes closer to the outer membrane by 2.5 nanometer, which we interpret as an osmotic effect, which is happening when you change the proton concentration across the membrane. So now it's the final stage of my presentation, which is now basically combining everything. And this is fluorescence lifetime image scanning single molecule localization microscopy. So again, let me show you our setup. That was what you already have seen. We have our pulse excitation laser. We have our very fast scan unit. We can then take scan images here. And then, as I said, we can use it also for single molecule localization microscopy. But now in the later stage, what we did is we have replaced our single detector here by a spot array. And this is something I would really like to advertise, because since something like 2-3 years now, these spot arrays became commercially available, and I think they will induce a small revolution in microscopy. So what you have here is a 23 spot array detector, so you can take small images at every scan position with extremely high speed, so that you can take basically with gigahertz repetition rate, and it's single photon counting. So and for every spot detector also you have the lifetime information. This is exactly what we need for image scanning microscopy. So we equipped our system with such a detector, and now we combined it with single molecule localization the following way. Let's assume again you have here your sample with sparse molecules distributed on the surface. We take a fast scan image, then you would see then these single molecule images here. Normally then you would localize these molecules, and that is the end of the story. So what we now do is, because we have this image scanning property now, we can apply this pixel reassignment, which is reducing the size here of my molecules by a factor of 2. And only after that I do the localization. So I'm gaining a factor of 2 for basically nothing, because the spot array detector is anywhere in the system. And to show how it works, it was the first in the presentation literature. Again, Tulane network, that is the standard single molecule localization. What we achieve here is 10 nanometer. And then with this image scanning trick, we come down to 5 nanometer. And it's my last slide, again, to show you also why lifetime can be super nice and important. This was then an application of our system to looking at the distribution of pre- and post-synaptic proteins in a synapse. It was together with the group of Silvio Rizzoli here in the University Medicine. And we labeled here HOMA1 protein and Bazoon with 2 different dyes. And the important thing is that the dyes have similar emission properties. The only distinction between them is the lifetime. So one dye, the Cy3b, has a lifetime of 2.8 nanosecond, and the ATO has a lifetime of 3.66 nanosecond. As you can see, there is quite some overlap, but using a very clever Bayesian the decision algorithm, we can easily distinguish between these the different kinds of molecules. And it is super important when you come down to such a resolution of a few nanometers, because then when you would do dual color imaging, you would have for sure chromatic aberration problems, which are completely absent when you use lifetime for doing the imaging. So with this, I'm at the end of my talk. I have, of course, to thank my whole group here in Göttingen. These are the active members of our group. Here are my alumni who took really big part in all this research, our collaboration partners, and especially I have to thank the European Research Council for generously funding my research. And thank you for your attention.
Thank you very much, Jörg. That's really fascinating work. So the floor is open for questions. Maybe let me break the ice and ask the first question. So in the second part of your talk, when you demonstrated, I don't know how you pronounce it, a meet and a geet, those two techniques. So the accuracy of the distance determination would be very strongly dependent on the orientation of your dye. So how do you handle that? Do you fix? Do you make sure that the dyes are fixed in certain orientations, or do you average over all the different rotations?
It's an excellent question. Yes, indeed. Yeah, when you look at the physics, then this coupling, the coupling of the excited state to the metal is very strong, orientation dependent, very similar to what you see when you do Fred experiments with donor acceptor molecules. There is also this mysterious kappa orientation factor. So what we do in our experiments, we always check by independent polarization resolved measurements, what is the orientation of our dye. And for example, for this example, what I have shown here, for these cancer cells, what we then found, it was with deep red stain plasma membrane dye. We were seeing that this dye is very flexible. So it is rotating very quickly. And we can use then this random orientation curve as a calibration curve. In other experiments, we had seen that other membrane staining dyes, for example, they have a preferred orientation parallel to the membrane or perpendicular to the membrane. But again, this is then done by a priori measurements. Typically, we use it in vesicles, in giant lunar vesicles for checking the orientation. And it is then figured in the data analysis. But it's a very good point. Yeah, you have to make sure a priori that you know what is the relative orientation of your dye. Yeah.
Okay, thank you. That makes sense. Okay, any other questions?
Hi. Thank you very much for the talk. It's a lot of information. I was wondering if, like with these GIT or meat measurements in the membrane, if single particle tracking has been done with that. See.
Yeah, I mean, not in the membrane, not in the membrane. So what we showed was that when you have a static sample, where nothing is moving, then you can get this super high resolution, even with single molecules. That is single molecule measurements, but with immobilized molecules on such a graphene sample. The problem with the membrane is that, of course, you always have lateral diffusion. So when you label here lipids in your in the membrane, then you have lateral diffusion, which is not so small, so in the order of 1 micrometer square per second. So that means that when you take a confocal microscope, then the residence time of a single molecule in your focus is limited to a few milliseconds. And this is probably too little to get enough signal for getting a resolution here of a few angstrom. Yeah, so this is the limitation. Of course, I mean, we are dreaming about an idea to use something like single molecule tracking, yeah, so active tracking, to do something like that we can follow a molecule, diffusing molecule in the membrane. And that would be, of course, a dream experiment, but it was not done so far.
Okay. Since this axial resolution would, I think with single particle tracking, it's difficult to get axial position accurately. Yeah, so yeah, that would be maybe a good a good thing to try.
Yeah, simply to give you some number, but I think it's quite important here for these measurements, so where we have here 2 angstrom or even 1 angstrom resolution, yeah, we had to collect something like a few million photons for getting this accuracy. That was a densely labeled sample, so we could measure with no problems. It was not single molecule, it was densely labeled membrane. And we needed a few million photons to get then the good bi-exponential decay for then extracting the 2 lifetimes for the upper and lower leaflet. Yeah. So this will not work with single molecules. No?
Yes. Yeah. So it's also that FCS method with meat that makes more sense.
Yeah, good point. I mean, we did it. This is published. So we combined this graphene-induced energy transfer with fluorescence correlation spectroscopy measurements for example, looking simultaneously on vertical membrane fluctuations and the lateral diffusion of lipids. So this is doable. This we did.
Okay. Yes. It would be nice to do that also with light harvesting complexes. Yes. But yeah, thank you very much, Prof.
Hello. Yes, Matthew, please go ahead. Yes.
Yeah, to add to that question, because I was a bit puzzled about the axial resolution of your setup of the meets, to be precise. Do you have like did you think, or have you approached the photon limit of this particular setup, the photon limited region of it?
Naja, sure. I mean, when you do single molecule measurements, of course, then you are limited by the photo bleaching of your single molecule. Huh? When we did this, as I show you, when I did this calibration curve, of course, we had tons of signals. So what we did, we had prepared here a dye-doped polymer film with a very dense labeling of fluorescent dyes here. So there was no signal restriction. And then we could simply here collect up to something like 30,000 photons, for example, per scan position. Yeah. And then we use this also this axial resolution is an estimate as a standard deviation from the mean. And this solid curve is simply a square root of n curve fitting. Yeah. So I think this is the defining curve. Of course, in the end, you are limited by how much photons can you detect from a given position or from a given molecule. This is then restricting how well can you then position it axially. No?
You also made mention of the fact that you had some aberration problems. How did you manage to how limiting can that be in this particular?
The good thing with MITE, when you only talk about axial resolution, this is here about axial resolution along the optical axis. The good thing with this metal-induced energy transfer, it is a lifetime measurement. So the good message here is that, aberration, I don't care at all. I have only to take a good lifetime measurement. Yeah, this intensity independent, and also how my lateral image looks like is not so super important. Yeah, so I simply measure the lifetime of something like here, this film, and it gives me the distance. Yeah. And
yeah, thank you. Thank you. That answers my questions. Yeah.
Okay, I think I can give time for another question. If there are burning questions, maybe two more.
So maybe as a side remark, if somebody in your community has any interest in any of these methods, we would be super happy for any collaboration or for assisting to setting something up or whatever. So please simply give me email, contact me. We are always happy when people then also use such ideas here.
Yeah, thank you for the invitation. I myself am quite interested, so maybe I should contact you separately about that. Because these are all fascinating techniques. More in line with what Francois has mentioned, our ideas of coupling it with FCS, maybe light harvesting complexes, things like that. But we have to give that more thought. Okay, these are very powerful techniques. So let me see, any other question? Maybe just a last question. So I was actually wondering about how low can one realistically go in the number of dyes? So is it really feasible to do single particle tracking using this technique? Let's say that we would like to have an actual resolution of, I think 2 nanometers is stretching it very much. But if you can think of 5 or 10 nanometers, do you think it's realistic to go down to the single molecule limit?
Also for static samples, yes. So we did it. I didn't show it here, but we did some samples with DNA origami and single molecule decoration, and we could show that we can go down on the single molecule level to a resolution of 1-2 nanometers. For a static sample, that is important. When you have now something like diffusing molecules in a lipid membrane, the really problem is here that they are diffusing out of the focus. And you have to do something like an active tracking. Again, here, by the way, there are very nice ideas by my colleague Giuseppe Viccidomini from Genoa, who is using sputter ray detectors for doing this kind of tracking. And this is on our agenda. We want to combine active tracking using sputter ray, using fast asynchronous scanning, and then to combine it with JIT or MEAT to get this very high Z resolution. But this is not yet realized. Yeah. But it would be, of course, I think it would be super attractive if you can track single molecules, let's say in a membrane or even a cellular membrane, and then also monitor its height with high accuracy. It would be the dream experiment, yes.
Definitely, yeah, that would be very powerful. And as you might know, we are also quite interested in the single particle tracking,
Yeah,
the real-time tracking. So
yeah.
that would be amazing. Okay,
Yeah,
well, yeah, so let's close here. Thank you very much, Jörg. That was really fascinating. And you're welcome to stay on the rest of the day, or yeah, as your own time allows. There might be a few other interesting talks later today, but thank you again for taking some time to contribute to our conference. It was great to have you here.
Thank you so much for inviting me.
Yeah, it was a pleasure to have you. Thank you very much.
Okay.
Right, so we are going to have a short break, and the next talk will then resume on the hour. So if there are more questions in the meantime, you're welcome to ask that, or you can just take a short break. So see you then again in a few minutes. Lawrence, I think you can already make the next speakers co-hosts and also give them the opportunity to test their slides.
Okay, let me do that right now.
Okay, great, thanks. Good morning, Tony. It's great to see you here. So our next session is going to start on the hour. You're muted.
Yeah, 10 minutes time. Sorry, yes, I was muted.
Yes, no problem.
There was a call yesterday and I didn't want to make any contribution. So yes, how's it going? I looked in on Tuesday and it seemed to be okay.
Yeah, we've managed to get quite a full program.
Yeah.
I'm quite on the last minute, so we're grateful for that. And yeah, the quality of the talks has been really good, I think, so far.
That's great. Yes, no, it's good. You've got a full program. That's right. Yes, I was looking at it. Just so many things going on. It's staggering. That's great. I mean, the whole of Biophysics Week seems to have gained momentum this year. And I was in the meeting in San Francisco in February, and that it's the first time in my living memory and theirs that they've not made 4,000 people, whereas normally this meeting is, way up at the 7,000, 8,000. So I just wonder whether people are not traveling for whatever reason, obviously financially in the States and with the government and the administration, and then they're using this way as a way of communicating.
Definitely.
Yeah.
Yeah, I think one of the reasons is that there are just so many conferences.
Yeah, that's true.
Also in biophysics, there's really a lot happening this year.
Yeah. That's right. I mean, I think again, this multidisciplinary side of it is really catching on. The International Science Council, which IUPAB is a member of, they are desperate to get multidisciplinary and cross and transdisciplinary science going. So we're trying to, capitalize on that as well. But yes, it's an umbrella under which a lot of people can stand, which is good. Yeah, great, good. Well, good for you and keeping it going in Africa too. I appreciate it. I see the emails popping up all the time, which is good. And getting the community together, and maybe we'll be able to be part of the meeting next year, which is and thanks for the suggestion. I think it's a great suggestion. Yeah, that's good. Is there anything else we can do for the meeting next year, the Congress, or is everything under control?
I think so.
Yeah.
Yeah, as I mentioned before, I think it's a great idea to host a symposium, maybe just one day before the Congress. So
Right.
that's an idea that I still want to discuss with the main organizing committee, because I think that would particularly be a way to enhance the biophysics component at this conference.
Like a satellite, like we did for the chemistry one in Kuala Lumpur. Yes. Well, that would be good, especially if you can get people, representatives from the various groups around the continent together as well. And that might start to produce some coherence. Why don't you think about kind of putting a plan together and send it to me, and I can circulate it and see what people feel, if we can support.
Okay, sure, I can do that. Yes.
Yeah. I mean, the issue you have, of course, is bringing people in person across Africa. It's a huge continent. And, travel is such a major component. You're not just jumping on a plane and being there in an hour's time. Things are very different. So that needs to be taken on board, I guess. But I guess if you had, a few movers and shakers and then made the thing open to the whole of the community, that would be good. I think that would be good.
Do you think we should consider making such a satellite meeting a hybrid meeting? Because that will enable most Africans to participate. Otherwise, there are always the financial constraints and visa problems and all of that.
Absolutely. I think that's the only way you can go, given the geography. I think that's the only way you can go. I mean, Europe's so much easier, of course. You can just jump on a plane, as I say, and be there. The States is more difficult, but people do travel. It's much cheaper there. But in your continent, it's just impossible. Latin America does it too. They've got a big community, as you know, out of Brazil, Argentina, and Chile, and they get together regularly, in fact, very regularly indeed. They've also produced a couple of special collections for biophysical reviews, two of them, in fact, and they're 15, 20 papers and reviews from people across the continent. And that brings people together as well, because they publish together across similar topics. So that also has enhanced them. So they're very active in that respect. But yes, absolutely, making hybrids as well. That I think would go down very well.
I think one of the things that we should do is try to
Hi, Lawrence.
Hi. To set a meeting with the relevant ISC unions relatively soon. I reached out for this particular meeting. I reached out to the president of IUFAR, so the pharmacologist.
Yeah.
Right, and it took more explaining than I thought it would as to what is the relevance to of biophysics and pharmacology. Right, I thought that was a point I would not have to sort of lobby for, but lo, I did. But I think sort of we need to get not only IUPAB and IUPAC, but the biochemists and then the pharmacologists, toxicologists, all these different unions that are sort of biophysics adjacent, if not biophysics dependent, to sort of get coherence, as you said.
Yeah. So on that point, IUPAP has a biological physics group, as you know. IUPAC has a biophysical chemistry. And in fact, the chair of that has just stepped down, but is currently, we are supporting her nomination to be one of the vice presidents of ISC. So again, pushing the interdisciplinary level at ISC, which they know about. We've told them about it. We go to all their meetings. So, but I think we could certainly involve them. You've got IUBMB, of course, coming to the Congress in 2027. So you've got the molecular biologists and the biochemists there. But there's no reason why you can't ask them to be involved. They all have these subgroups, which are quite big. They organize their own meetings.
Even the mathematical union. I mean, that's why I wanted to get Anita Layton to.
Yeah, sure. Yeah, I saw that. Yeah. No, for sure. And you get representatives from these. We do have a cross representation with IUPAP, as it happens, and with IUPAC on IUPAP. So it's one of the things I've been pushing is to talk to other unions at that level. Of course, we also do it at the society level, but yes. Sure. Yeah. Well, yeah, Chad, why don't you try and get that together and kind of flesh out something and come back to us, and we'll see what we can do about that. It is going to be a heavy year for us, of course, because we've also got the Congress in Berlin, which unfortunately is just a few weeks before the Congress in
Genoa,
which is a bit of an issue, but we'll try and get around that in some way if we can. Yeah. Why don't you try that? And of course, we'll help you with making the connections with these people, because we know the presidents of all these unions and all the subgroups as well. But certainly we can help out and maybe get a few people down from Europe down to you as well, which I'm sure we can do. There are one or two people who have expressed an interest in coming down to you next year anyway. So you just let me know what you envisage. Okay. That would be great.
Certainly. Yeah. I'll make work of that.
Yeah, sure.
Okay, thanks.
Right. Yeah. Okay, I think let's get ready for the next session.
I'm going to step back. I'm going to go offline. Well, I'll be here, but I'll turn my mic off and turn my camera off and go with that. Okay.
Right. Thank you. So the first speaker of the next session is Franco Conradi. Franco, you can start to share your screen and let's check if everything works. So this is going to be a full session, 4 speakers with very interesting topics. Right. Lawrence, I would like to request if you could pause the recording because the speaker and also the next one are going to show some unpublished results.
Okay, let me I should have been. Let me. I'm working on it. I'm on a different device at the moment.
Okay, well, the first part of this talk is already published. So I think let me go ahead in the meantime. So the next speaker is Franco Conradi from the University of Pretoria, and he's going to talk about multi-time scale fluorescence correlation spectroscopy of the main plant light harvesting complex during aggregation